Okay, so I want to start this one with a question, and I want you to think about it honestly. When was the last time you uploaded a profile picture somewhere, or signed up for a newsletter, or bought something online, and the website showed you a loading spinner for like 30 seconds, and you just kind of stared at it? And then you started refreshing, and then you just left. Right, because you assumed it was broken. But here's the thing, and this is the uncomfortable engineering truth we're starting with today. That experience wasn't just bad UX, it was a symptom. It was your browser telling you that somewhere on a server, a thread is sitting there, blocked, holding a connection open, consuming memory and CPU, waiting for a bunch of side effects to finish, resizing the image, sending the welcome email, updating the search index, notifying the shipping department, all of it in a chain while you just wait. And the really interesting question isn't, why does that feel slow? The really interesting question is, why did we build it that way in the first place? So today is about that. Today is about the architectural pattern that separates systems that crumple under load from systems that just keep going. We're going to talk about asynchronous systems, about the profound power of the word later. I want to start by giving you the foundational principle, and I'm going to call it the first principle of this whole video. Time is your most expensive resource, and you need to decouple it. What I mean by that is this. In a traditional synchronous system, what's called request-response, the user is locked in a kind of dance with the server. They send a request, the server does a bunch of stuff, the user waits, the server responds. They're tethered together in time. If any single link in that chain is slow, the email provider is down, the image resizer is backed up, the database is under load, the whole chain stalls. Every single user who happened to sign up in that moment sees that spinner. This is called temporal coupling, and it is genuinely the enemy of scale. So what we're going to talk about today is how we break that coupling, how we take that 30-second chain of work and push it into the background. We're going to look at queues, things like SQS and RabbitMQ, and we're going to contrast them with streams like Apache Kafka. We're going to talk about backpressure, which is honestly one of the most important and underappreciated concepts in distributed systems. And we're going to talk about some failure modes that will absolutely bite you if you don't design for them. Let's go. Okay, so before we get into infrastructure, I want to give you the mental model, because the mental model is everything. If you internalize this, the rest of it just falls out naturally. Synchronous communication is a phone call. Think about what that requires. For a phone call to actually work, both people have to be available at exactly the same moment in time. If I call you and you're in a meeting, the communication fails. If I call you and then I need to go look something up, you're sitting on hold, doing nothing, unable to call anyone else. You are fully, completely blocked. We are coupled in time. Asynchronous communication is a text message. When I send you a text, I genuinely do not care if your phone is off. I don't care if you're busy. I don't care if you're on a plane. I send the bits and then I go back to my life. I can cook dinner. I can have another conversation. I can go to sleep. You will see the message when you have the capacity to handle it. You respond on your own terms. And here's the mapping to software. Most junior to mid developers build phone call architectures. Two services need to talk. Service A makes a REST call to Service B. Hey, Service B, please do this right now. Okay, Service A, I'm doing it. Give me a second, wait for me. And if Service B is slow, or if Service B crashes, Service A is just stuck. The more senior approach, and I don't mean that in an elitist way, I just mean the approach that scales, is the text message architecture. We call this event-driven architecture. Service A doesn't call Service B. Service A publishes a fact into the world. It says, essentially, hey, a user just signed up. Here's the data. I'm done. Goodbye. It drops that fact into something called a message queue, and it immediately returns to the user with a success response. And then service B and service C and service D, any number of services, they are subscribed to that queue. They pick up the message at their own pace, in their own time, and they do their work. This shift from calling to messaging is genuinely how you build systems that survive a 100x traffic spike without crashing. And let me explain exactly why. So why does this pattern actually help at scale? It all comes down to one concept: the buffer. In a synchronous system, your capacity is fixed by your resources. If your web server has 100 threads, you can handle 100 concurrent requests. The 101st user arrives, 504 gateway timeout. Sorry, the system is full. But in an asynchronous system, we introduce a message queue that acts as a shock absorber between the producers and the consumers. Let me give you a concrete example. You have a producer. Let's say it's your web server, and you have a consumer. Let's say it's a background worker that sends emails. Normally, your web server generates 10 sign-up events per second, and your worker processes 10 emails per second. Queue is basically empty. Life is perfect. Then, you get featured on the front page of Reddit, your hug of death moment. Now, suddenly, your web server is generating 1,000 events per second. In the synchronous world, 990 of those users would see errors, threads exhausted, system overwhelmed. In the asynchronous world, those 990 messages go into the queue. They sit there safely. Your web server doesn't slow down, doesn't crash, doesn't block. It just says, "Great, message received, stored safely, you're good," and returns a success to every single one of those users instantly. Your consumer is still processing at 10 messages per second. It's behind, sure. The welcome email might take 10 minutes instead of 10 seconds, but the system didn't crash. Not a single message was lost. This is called load leveling. You take a massive, sharp, unpredictable traffic spike and you flatten it into a long, sustained, manageable stream of work. You are explicitly trading real-time latency for system stability. And in most cases, for most workloads, that is a profoundly good trade.
Now, here's where I want to spend some time, because this is where a lot of confusion lives. There are two main tools in this space, and people constantly conflate them, but from first principles, they solve fundamentally different problems. The first is the task queue. Things like SQS, RabbitMQ, Celery. Think of this as a post office. You have a specific piece of work to do. Resize this image. Send this email. You write it on a slip of paper, put it in an envelope, and drop it in the mailbox. A worker at the post office picks it up, does the job, and then, this is the key part, destroys the envelope. It's gone, done, processed. This is great for work distribution. If you have 1,000 images to resize, you spin up 10 workers, and the queue deals messages out to them one at a time. Each image is processed by exactly one worker, exactly once. The semantics are, I have a job, someone please do it, once it's done, it's done. The second tool is the message stream, Kafka, AWS Kinesis. Think of this as an immutable append-only log. Kafka isn't a post office, it's a long, infinite scroll of paper. When a producer writes a message, it gets appended to the end of that scroll, and it stays there. It is not deleted when it gets read, it lives on the scroll. Instead, each consumer has a pointer, called an offset, to track where in the scroll it's currently reading. It reads at its own pace. And this unlocks something really powerful: multiple independent consumers. Your email service can read the scroll to send welcome emails. At the exact same time, your analytics service reads the same scroll to count signups for a dashboard. Your fraud detection service reads it too. They don't interfere with each other because they each have their own pointer. And then there's replayability, and this is my favorite part. Imagine your analytics code had a bug and produced incorrect counts for the last 2 weeks. With a task queue, those messages are gone. You can't recover them. But with Kafka, you just move your offset back to 2 weeks ago and reread everything. the data's all still there. You replay the history and recompute correct answers. So the mental model for choosing between them, if you have a specific job that needs to be done exactly once, a task queue. If you have a fire hose of events that multiple systems need to observe, or you need historical replay, Kafka or a stream. Now I want to spend a minute on Kafka itself because it's a genuinely beautiful piece of engineering, and most people attribute its performance to the wrong thing. They assume it's fast because of some clever networking magic or exotic in-memory data structures, but actually, no. Kafka is fast because its designers deeply understood the physics of how computers actually work at a hardware level. Sequential I/O. This is the first insight. Kafka never goes back to the middle of a file to modify something. Every write is an append to the end of the log, and this matters enormously because even a spinning hard disk, which mechanically moves a read head, can sustain hundreds of megabytes per second of sequential throughput. It's random access that kills you because that requires the head to physically seek to different locations. Kafka sidesteps this entirely. Zero copy transfer. This is the second insight, and it's subtle. In a traditional system, when you want to read data from disk and send it over the network, you typically make multiple copies. Data moves from disk into kernel space, then into application memory, your Java process, then back into kernel space, then out to the network card. That's a lot of unnecessary work. Kafka avoids this by using a mechanism called send file, sometimes called zero copy, where it tells the operating system, take these bytes from the page cache and push them directly to the network socket. The Kafka broker process itself is largely bypassed. The data never has to land in application memory at all. I should be precise here. It's not that zero copying happens. The OS and the network card's DMA engine are still involved, but Kafka eliminates all the unnecessary copies between kernel space and user space that a naive implementation would do. And then there are partitions. This is how Kafka scales horizontally. A single Kafka topic, like user signups, isn't one big file. It's split into multiple partitions, and each partition can live on a different physical machine. So you can have 50 partitions spread across 50 brokers with 50 different consumer instances, each reading their own partition simultaneously. This is how LinkedIn, the company that created Kafka, processes literally 7 trillion messages per day through it. But there is a consistency cost here you need to know about. Kafka only guarantees message ordering within a single partition. If you need message A to always be processed before message B for a given user, you have to make sure both messages land in the same partition. The standard way to do this is to use a partition key, typically something like user ID, which ensures all events for a given user always go to the same partition and are always processed in order.
Cool. Now we get to the most important concept in this whole video, and I'd argue one of the most important concepts in distributed systems: backpressure. Let me give you a plumbing analogy because it's very apt. Imagine your web server is a high-pressure fire hose. Your database is a kitchen sink. If you connect them directly with no buffer, the sink overflows. Floor gets wet, system crashes. So you put a tank in the middle, your message queue. It collects the water. Good. But now, what happens if the fire hose keeps running and the tank itself fills up? Eventually, the tank overflows. You run out of memory, you run out of disk on your Kafka brokers. Something breaks. Backpressure is the mechanism by which the consumer signals to the producer, "Whoa, slow down, I cannot handle any more right now." And there are basically 3 strategies for handling this. Strategy 1. Drop messages. When the queue is full, new messages are simply discarded. This is called a lossy queue. It sounds terrible, but it's actually the right choice for certain workloads. Logs, metrics, analytics data, where the occasional dropped data point doesn't matter. You would never use this for financial transactions. Strategy 2. block. The producer tries to enqueue a message, the queue is full, so the producer thread waits, blocks, halts. And here's the trap. Wait, what did we just do? We took our beautiful asynchronous system and we turned it back into a synchronous one. If the queue is full, the web server thread is now blocked. The user is seeing a spinner again, and we're right back where we started. This feels like a safe fallback, but it can silently kill the whole benefit of going async. Strategy 3. Dynamic scaling. When the queue starts filling up, you automatically spin up more consumer instances, more workers, more capacity. This is what AWS Lambda autoscaling does, what Kubernetes horizontal pod autoscaler does. But, and this is the trap that trips up even experienced engineers, what if all those new consumers suddenly start hammering your database at once? You've just moved the bottleneck. The queue was the victim, and now the database is. And databases often fail less gracefully than queues. This is why a senior engineer's mental model here is every system has a maximum sustainable throughput. You need to design for what happens when you exceed it. The right pattern is to have a dead letter queue, a DLQ, where messages that can't be processed get parked for manual review rather than letting them crash the whole system or silently disappear. Design for the failure case, always. Okay, hard truth number 2. Distributed systems are unreliable. When a consumer picks up a message from a queue and starts processing it, 3 things can happen. 1, the worker crashes before it finishes. 2, the worker finishes the work, but the network dies before it can send the acknowledgement back to the queue. 3, everything works perfectly. Because of scenarios 1 and 2, most production queues, including AWS SQS, use a delivery guarantee called at least once delivery. The queue will keep resending a message until it gets an explicit acknowledgement that the message was handled successfully. This means in the real world, your consumer will occasionally receive the same message twice. The network will hiccup, servers will restart, timeouts will happen. Now think about what this means for your application. If you're sending a welcome email and the message is delivered twice, the user gets 2 welcome emails. Annoying, embarrassing, but okay. If you're charging a credit card $100 and the message is delivered twice, the user gets charged $200. That is a disaster. To protect against this, your consumers must be idempotent. This is a first principle requirement of any serious async system. An idempotent operation is one that produces the same result whether it's executed once, twice, or 100 times. Processing the same message multiple times has no additional side effects beyond the first time. How do we achieve this in practice? With an idempotency key. Every message should carry a unique ID. Before your consumer does any work, it checks, have I already processed a message with this ID? If yes, send the acknowledgement to the queue, stop, do nothing, you're done. If no, do the work, then record this ID in your database as processed. If you skip this, your asynchronous system is a corruption engine. It's not a question of if a message will be delivered twice, it's a question of when. Build for it. I want to talk about one more specific failure mode because I see this bug introduced by developers constantly. It's subtle, it looks totally harmless in a code review, and it will eventually cause data loss. Imagine you're writing sign-up logic. Step 1, save the user record to the database. Step 2, send a user signed up event to the queue. This looks fine. It is not fine. The problem is that Step 1 and Step 2 are not atomic. They are 2 separate operations touching 2 separate systems. If Step 1 succeeds and then your server crashes before Step 2 executes, the user exists in the database, but the welcome email is never sent. The analytics event is never fired. The downstream systems never know this user exists. Silent inconsistency. If you flip the order, step 2 first, then step 1, and the queue write succeeds but the database write fails, you've now sent an event for a user who doesn't exist in your database. Also broken. The solution to this is called the Transactional Outbox Pattern. Instead of writing to the queue directly, you write the message into a special outbox cable in your database as part of the same database transaction as your user record save. Because it's a single transaction, it's atomic. Either both the user record and the outbox entry are committed, or neither are. You get the full ACID guarantees of your database. Then a separate background process, sometimes called a relay or a CDC connector, reads that outbox table and pushes the messages to the actual queue. It's a bit more infrastructure, but it completely eliminates the dual write problem. You've bridged the gap between your database truth and your messaging system in a provably consistent way. Look, I've been fairly enthusiastic about asynchronous systems for the last 30 minutes or so, but I want to be honest about the complexity tax because it's real. Asynchronous systems are genuinely hard to debug. When a user says, "I never got my welcome email," you can't just open one log file. You have to trace the event across multiple systems, from the web server that produced it, to the queue that stored it, to the worker that consumed it, to the email provider that tried to send it. You need distributed tracing infrastructure just to answer basic questions. That's video 14. And asynchronous systems are hard to reason about. You have to think about out-of-order messages. You have to think about retry storms. You have to explain to your product manager why the dashboard doesn't update instantaneously. Eventual consistency is a hard sell to non-engineers. So here's my honest heuristic. If you can solve the problem synchronously under 100 to 200 milliseconds, just do that. Don't reach for Kafka. Don't add a message queue just to update a user's last seen timestamp. The complexity is not worth it. Use async for tasks that take more than a few hundred milliseconds. Image processing, PDF generation, video transcoding. Use it for any third-party API call where you don't need the result immediately. Emails, Stripe webhooks, Slack notifications. Use it for high-volume data streams where you can tolerate some latency. Logs, analytics, audit trails. Use it for decoupling services in a large organization where teams need to evolve independently. If none of those apply, just make the synchronous call. Premature async is its own form of over-engineering. All right, let's wrap this up. What I want you to take away from this video isn't a list of tools. It's a shift in how you think about systems. Asynchronous design is fundamentally about respecting the reality of the physical world. The physical world has network lag. The physical world has servers that crash. The physical world has unpredictable spikes of traffic. A synchronous, tightly coupled system treats all of these as exceptional conditions, things that shouldn't happen. An asynchronous system treats them as expected conditions, things it was designed for. Let me give you the 4 principles I want you to carry forward. Decouple time. Don't make the user wait for side effects. Give them a success response and do the work in the background. Their email will arrive. Their image will be resized. Just not in the next 30 seconds. Use the right tool. SQS and RabbitMQ for discrete jobs that need to happen once. Kafka for high-volume event streams that multiple consumers need to observe or that you might need to replay. Build for failure at the message level. Your consumers will receive duplicate messages. Make them idempotent with idempotency keys. Use the outbox pattern to prevent data loss from dual writes. Use dead letter queues to catch messages that persistently fail. Manage the flow. Understand your system's maximum sustainable throughput. Design for what happens when you exceed it, not just for the happy path. When you shift from synchronous to asynchronous, you are shifting from a brittle system to a resilient one, from a system that breaks under pressure to one that bends and absorbs it. That is what you're actually building when you introduce a message queue, not just background processing, a fundamentally different relationship with time and failure. In the next video, we're going to go much deeper on one thread from today: engineering for failure, retries, and idempotency. We touched on it here, but there's a lot more to unpack. We're going to look at the mathematics of retry behavior, specifically exponential backoff and jitter, and why naive retry logic can actually make a failing system worse rather than better. We'll talk about how to build systems that are genuinely self-healing, that expect failure as the default, not the exception. That's up next. See you in video 12.